It is estimated that the F-35 Lightning II Joint Strike Fighter program will cost over $1.7 trillion to buy, operate, and sustain. That makes it the United States Department of Defense most expensive weapons system program ever. As such, getting the most return out of each F-35 fighter for the DoD is of the highest priority. From the development, manufacturing, and sustaining phases, there is a concerted focus on F-35 lifetime and doing whatever possible to extend it. Active infrared thermography is one method being used to detect defects at the smallest level as part of the F-35 Joint Strike Fighter program. However, beyond jet fighters, automobile and component manufacturers, electronics and semiconductor developers, aerospace companies, and battery developers are just a few of the industries that are using active thermography, non-destructive testing technologies and techniques to optimize product performance. In this episode of the Thermal Review, we explain the difference between passive and active thermography and introduce the different techniques for performing active thermography, non-destructive testing. Marcus.
Yep.
Good day. How are you?
Good.
Good to be with you again in this episode 4 of our podcast series.
Yeah, hard to believe we're already on episode 4.
I know. It's great, though, that we're able to pull this together. And so far, it seems like the feedback we're getting is positive about our discussion points so far. I'm really excited about today's topic. I don't know how you feel about it.
Very excited because it's a really interesting one, I think.
In fact, for those of you who have dialed in and are viewing the video of this podcast, we're sitting outside of the Mobitherm non-destructive testing lab. And you can kind of peer in there and you'll see different apparatus, cameras, excitation sources, displays that are utilized as part of the lab here at Mobitherm. And we'll talk probably a little more about that later. Marcus, maybe as some background, you can tell us a little bit about, I mean, I know the answer to this already, but for our listeners, your history as it pertains to infrared non-destructive testing.
Yes. So as probably our viewers know, we have been in business since 1999, almost 23 years, starting in October. And we have been doing thermal imaging shortly after we started the company through our connection with FLIR. And then we were actually introduced to a partner company in Germany doing NDT test systems, and they were looking for a partner, and we kind of greeted each other and learned more about that technology. Up until then, we were just doing passive thermography, which we're going to be explaining further a little bit later. And so this active thermography method, which is non-destructive testing, or one of the possible non-destructive testing methods, which there are many of, changes the game a little bit because we're actively exciting a part that is typically what we call in equilibrium, right? So it's essentially cold, or it's at room temperature on all ends. So if you were just to point a thermal camera at it, you would just see a kind of like a gray mush. There's nothing of interest there to exploit. To change that is to just excite the part thermally on some level, and this could be done with different excitation methods, and essentially provoke some sort of a thermal response from the material, and also going into the depth of the material, and creating a thermal wave on the surface that penetrates deep into the material and comes back out of the surface, and that we can kind of discern changes in the material densities or uniformities in there, find defects such as delaminations and cracks and voids and foreign material inclusions and all those kind of things that are undesirable in the manufacturing process, especially of very expensive aircraft components.
Yes. I teased a little bit that I know the history with regards to Mobitherm being introduced to this infrared non-destructive testing technology, or this active thermography, because I was at that time, I was actually working for a very large thermal imaging camera manufacturer. In fact, the largest commercial infrared camera manufacturer. And we, as a company, and I still believe this, built the best infrared cameras on the market. However, there were applications that required just a little more than what we could provide as a manufacturer to tease out the defect, if you will. And we had heard about this infrared non-destructive testing or active thermography, and we had actually dabbled in it ourselves and tried to become experts at it so we could solve our customers' problems. But quite honestly, it was beyond what we could do because it required a certain level of focus, and in some ways it was almost like an art. And we found as a manufacturer that we just could not do this directly ourselves. So interestingly enough, I knew Marcus because of a friend that we had in common who actually came to work for us. And Marcus seemed like the perfect organization to introduce to this German organization to learn this capability. So we would have someone as a manufacturer who we could refer customers to so that their problems could be solved beyond what we could do with passive technologies. And what was this like? How long ago was this? You and I, Marcus and I actually...
15, 17 years ago.
Yeah, we actually made the trip together.
Right.
As a side story, one day, flew into Germany, where did we fly to? I can't even remember. Hamburg. Yeah. Rented a car, drove out to this German supplier, got spun up on their capabilities and technology, hopped back in the car, drove back to the airport, and came home. Yeah. And we're both based, well, he's in California. I was in Seattle at the time. So yeah. We're both West Coast. But anyways, kind of a funny joke. But
not sure why we did that on one day.
I'm still not sure either. For some reason, we felt this urgency. We got to get out there and learn this. But there was, the thing is, I guess the point that I wanted to make is there was a need in the market for this capability, for this technology. And there were some new advancements in infrared non-destructive testing, specifically lock-in technique that we'll get into that nobody really had. Right. But the customers had been introduced to it. They understood, based upon just lock-in technology used in other sciences, how effective this could be for, again, teasing out these very small defects or imperfections in certain targets. And there was nobody out there. So Mobitherm came on board, spun up, and now you guys are like one of the leaders here. I guess we are, since in this lock-in capabilities here in the United States, which, anyways, that's kind of a long history.
Right. It is also, I mean, it's a very fascinating technology with a lot of promise and capability. There's still, even though it has been around on an academic level, I think for 25, 30 years already. But the adoption has been still very slow in the industry because there wasn't, there weren't that many companies out there. There wasn't that much expertise out there, and also the standards kind of limped behind, right? So there's the ASNT, the American Association for Non-Destructive Testing, and so since the adoption was so low, there wasn't a huge push towards getting standards out for that technology. And the de facto standard in the industry still kind of today is ultrasonic testing, ultrasonic NDT or UT. One challenge with that is that the workforce is trained and certified in that industry, in the non-destructive testing world, on UT. And so it's not as simple as just purchasing an NDT system of a different kind, and that's true for anything, whether you switching from UT to X-rays or magnetic particle testing or whatever else the case may be. The same things apply, the same rules apply for thermography. So you have to also consider training up your workforce and getting them recertified on a different technique. And they have to also do these continuous educational units. So they have to keep up to speed and put so and so many hours in a year to go to conferences and use that equipment and document all of those things. So that comes with it. And what also was so far kind of a hindrance on the adoption side, I think, was also the cost of the cameras were so exorbitantly high, where we now have solutions that drop way in price and make this technology more accessible, especially also with the advent of the use of thermoplastics and carbon composites versus metals. For metals, we always need the high-end cooled cameras, high-speed, very expensive equipment, whereas for the thermally slower responding materials such as carbon composites, which are kind of taking over the metals and replacing them slowly in the aerospace industries and other industries like racing, automotive, and so forth, it becomes more feasible to use less expensive camera equipment, such as these microbolometers, uncooled cameras, which then significantly impacts the system price and makes this more accessible.
Yeah, it's definitely opened up additional applications, new markets, industries, and solving problems that couldn't be solved previously with passive thermography, which, again, by way of review, passive thermography is no excitation, right? You're just looking at what the environment is producing,
right?
Thermally.
Right, the self-heating of something. Like if you're looking at an electrical motor that's running, it's self-heating, right? It has heat losses, and that creates a thermal contrast on the motor, right?
Yeah.
Some parts are warmer than others, and that's your contrast essentially in the thermal image, where it's not present if you just have a piece of material lying around.
So most of the thermography that people are probably familiar with is, from an industrial perspective, that is let's say the example of inspecting a substation with a handheld infrared camera and passively, if you will, scanning the targets. Could be disconnects, switches, transformers, breakers. They're all heating kind of on their own, or not heating on their own kind of naturally. You're not sending any other additional energy to those targets or at those targets.
Right.
Yeah.
Right.
Whereas active, as you described earlier, I thought quite well about this wave. Maybe you can describe that again. And
right. So there's different methods that we can go into further later, but there's what you mentioned before, a lock-in method that comes from the old radio days. The idea there, or the invention around this, was that there were radio waves that were out there, and people were trying to receive these radio signals from a very far distance. And the issue typically was if the radio signal was at the noise floor or below the noise floor, you couldn't extract that signal anymore. It was just gone, non-recoverable. And somebody, and I don't know the name right now, came up with the lock-in thermography. I'm sorry, not lock-in, the lock-in technique rather, in the radio wave industry, if you will. And they were basically saying, we know what the excitation frequency is, or the carrier frequency. Since we know that, why don't we just look for signals that match that frequency? If it's your radio station 98.7 megahertz or something, you could essentially lock into that signal because the carrier frequency is known. Even if the signal is buried below the noise floor, you could then amplify only a frequency around, basically create a bandpass filter that's very, very narrow and only amplify over and over again that signal. And eventually what you will see over many, many cycles, that signal will grow above the noise floor, and now you can actually extract it and do that. And we're doing the same thing on the thermography side of thing. We're doing this though on a pixel by pixel basis. It's a little bit of a mind warp to get your head around this, but it's done on a pixel by pixel basis in the thermal camera with a heat stimulus. So we know the frequency of excitation on the heat stimulus, and we can essentially extract changes at the rate of heat that is below a noise floor of a camera. And these cameras are already extremely sensitive. Those cooled cameras, they can be 0.018 degrees temperature changes. So with lock-in, we can actually, so that's millikelvin range. We can go into the microkelvin range and pull signals out. So that gives us the ability to, what we say, it's almost thermal radiography. We can literally, indirectly see inside the material what's happening, even though it's really just all manifesting itself on the surface.
Yeah.
But we're able to pull that information out now because we know the frequency of stimulation.
Lock-in is amazing technology. And again, that was one of the things that drove us to create this partnership years ago, because the market or industry and customers were very interested in it because they were familiar with it from electrical radio wave analysis, like you were describing.
Electrical engineering, essentially.
And then learning that, you can apply the math the lock-in math, if you will, to thermography and tease out again, because you're reducing that noise level to nil.
Yeah.
Almost. It's amazing. I'd like to talk a little bit about excitation sources, and because there's various out there. We talked about
Right.
lock-in,
Right.
and there's sources for that. I'm wondering if you're dialed in visibly, you probably notice there's an additional chair here with us, and we actually have a guest for today. And you mentioned something earlier about training workforce. Well, you have expertise in folks who are trained up in active thermography here at Mobitherm.
Right.
Yeah.
Right.
Do you want to introduce our guest? Should we invite him on?
Come on in, Nathan.
Hello. Thanks for having me on today.
It's good to have you here. Welcome.
Yes, thank you. So I'm Nathan, and you can see the amazing lab we have behind us. Basically, that's kind of my playground where customers are sending us all kinds of different parts. And sometimes, they know what defect you're looking for. Sometimes that's the question. And so we have many different excitation sources, methods, post-processing techniques that we use back there to basically help the customer dial into their specific needs, and we can get more into that. I'm doing the feasibility studies back here. All the methods that you have basically just mentioned already, we basically employ that back here in real time.
So let's back up a little bit. What? Let me ask you. I have the IRNDT experts here now, so this is awesome. I'm a passive expert. Backing up just a little bit, what are the different? Let's talk about techniques and then excitation sources. So we've already talked about lock-in. What are some other techniques for infrared non-destructive testing?
Right. What have you learned?
No pressure, Nathan.
Yeah, quiz that. So it's kind of the principle, like you mentioned a little bit. I'm going to back up a little bit. We want to get a heat wave into the part. Okay. It's kind of a call and response relationship. So we're basically issuing a call in the form of this heat signal, and we're reading with the thermal camera how that part is responding. The lock-in is that frequency element where you're periodically exciting it. You're basically doing like waves, and you have that frequency component to the analysis. Other methods include basically like a simple on-off excitation that's referred to as step thermography or transient thermography, where you're basically, it's almost like, you can think of it like a lock-in, but just for one cycle.
Okay.
You're basically just heating it up and cooling it off, and that whole cycle of heat up, the heat up and cool down phase can be very insightful. You can read a lot, about the material and what's going on under the surface just from that. And then even like the more condensed version of that, you can do a flash thermography, where basically that whole process of getting the heat wave in, you can treat it like an instantaneous excitation, because you have like a big flash going off, like, almost like picture day at school, except, way hotter.
Okay.
You're flashing apart, and then you're watching that cool down like immediately afterwards. It's sort of the same principle, where basically as the material is cooling down, subsurface differences, density variations and defects, things like that are starting to show up once that heat wave comes back, and you can start to see it with the IR camera. There are other methods, but it's basically that core principle of reading the response from whatever heat input you're putting into it.
Okay, awesome. And so, let's talk now excitation sources. So we talked about these techniques, the lock-in, transient, and the pulse or flash.
Yeah.
So, what are the different ways you introduce heat?
Yeah, so there are, a lot of ways you can get creative. What's important basically is like the repeatability. You want to do this scientifically. In theory, you just got to heat it up somehow.
Yeah.
You could even theoretically use like a heat gun or something. But the problem is, once you start doing stuff like that, it's just a little hard to wrangle. So common excitation sources could include halogen lamps. These are just basically you turn on an array or a single lamp source, and that light signal actually has a lot of heat. If you hold your hand in front of it, it starts getting pretty toasty pretty quickly. You can excite things with vibration. So this is not really, the vibration itself isn't, producing heat. It's the friction that as that vibration wave travels through the material, certain things start to, rub together and heat up, and you can see that with a thermal camera. You can do induction heating. That's basically using like a magnetic coil, almost like your induction stovetop, to basically, if you have a conductive material, it starts to excite that, heat it up. So, I mean, there are so many different ways. I mean, I don't know if I've missed any of the
How do you do, Marcus?
big ones.
Yeah, very good. I mean, yeah, we're getting into the more exotic excitation sources. It's mainly material dependent, as you said.
Exactly.
Like if you have something metal, we would choose different excitation sources than if it's non-metals and those kind of things. Really, it really depends on how the material responds to a stimulus. The other thing, I mean, there's some really exotic ones. You could use microwaves. You can use lasers, which we do on semiconductors sometimes, or something like this. And I mean, you can go as simple as holding an ice bag behind something and actually cool things down rather than heating things up. But that's really not a very, very scientific version of it. But I've done that on some parts before, kind of a thing. So yeah, it really is material dependent. I would say in aerospace, 80% of all applications are either halogen or flash.
Okay.
That's like the majority of applications that we cover.
It's very repeatable, basically.
Gotcha. And that's because the materials typically used in the aerospace are.
If it's metal, we typically use flash, but we can also use flash on non-metals, even carbon composites. For anything that is thermoplastics, carbon composites, anything surface and near surface damage. So this could be like impact damages from hail or from tool drops or something like this, or subsurface delamination sort of things, or any sort of very thin airfoils with foam cores and those kind of things. Flash works pretty well. It gives you a very quick and crisp sort of a response. But to understand that is also that on carbon composites or thermoplastics, there's a penetration depth limit to flash, because the full energy, our flash head, for instance, is 6 kilojoules. You can literally take the hair off your forearm if you don't watch out, or peel back a layer of material and then remove the N out of the NDT. And so you have to watch out with that. It's pretty violent, but it unloads the full energy of 6 kilojoules in 2 milliseconds.
Wow.
So that's great for creating a large delta in temperature, but at the same time, it's also not allowing that heat to penetrate deep into material that has a large heat capacity. So it spreads laterally, and that makes up that's the physics behind it that basically prevents it from penetrating deep. So that's when we typically switch over to halogen, because it's much softer from the heat input.
Okay.
It's not that violent, and we can have the lamp on for 30-40 seconds without significant heat up of the surface. It could be 8-10 degrees over ambient, and that's enough. We don't need more than that. Sometimes even 2 or 3 is enough. But we can penetrate deeper. We can get to 5, 6, 7 millimeters. This is about the top end in terms of penetration depth. If you needed anything deeper, we typically at that point refer back to ultrasound, X-ray, CT, some other method, because it's just, we have to recognize the limits of physics. We can't bend physics, at least not yet.
Yeah. Not yet. The ultrasonic or ultrasound excitation that's an interesting one. Is there a particular material or materials where that works best? That's my first question. My second question is, can you use the vibration for like lock-in technique? Can you modulate it, or is
right? So ultrasound thermography, or vibrothermography, as most people know it that have some knowledge of this, has been around for a very long time. It is great typically for finding delaminations and cracks in particular. The simple or traditional vibrothermography is really just turning on an ultrasonic. It's usually a modified weld head. Could be 400 watts, could be up to 2 kilowatts, and it's vibrating anywhere between 20 and 40 kilohertz, depending on what horn on there, or transducers on them, and the construction of it. There's some drawbacks of that. You have to put quite a bit of ultrasound energy in it, and it's really the only non-destructive test method under the thermography umbrella that is not considered non-contact, because now you actually have to touch the part.
Okay.
Usually it's just the camera and some heat wave through air on some level. So it's contact. So you have to make contact with the part, which sometimes is a challenge. It depends on how fragile is the part. How can you position the horn? If it's a very complex shaped part, it's a bit difficult sometimes on the curvature to couple something in. And then also the coupling side is under a lot of stress. So if you have a brittle part, we have had some ceramics, the ultrasound energy can actually cause damage if you're not careful.
Okay.
So then there's a more sophisticated version, which is lock-in vibrothermography. And that's the idea that you brought up, is to say, why not combining lock-in technique with ultrasound? The challenge with that is that the ultrasound vibration is between 20 and 40 kilohertz typically. The problem is you can't lock in at such high frequency with a camera that runs 100 frames per second. That's a bit of a challenge.
Yeah, okay.
People that understand electrical engineering and sampling frequencies will understand, like the Nyquist theorem and all those kind of things, where you're supposed to have at least 4 times the frequency of sampling versus what you're trying to sample. Like, for instance, if you're sampling a 10 hertz signal, you have to have at least 40 hertz to get sufficient number of points sampled on the sine wave. And that only applies to a true sine wave. If you have a distorted signal, that doesn't apply anymore. You have to have 10 times.
Okay.
So in these ratios, it becomes very clear that we can't run a camera at 100,000 frames per second to accomplish this. So what we do is we actually we modulate the output power of the ultrasound create an amplitude modulated signal, where the amplitude modulation goes at a lower frequency. It could be 2 hertz, could be 10 hertz. Now we can start to lock in to the changes in amplitude or the energy that's being put into the part, while the vibrational component is still at 20 to 40 kilohertz.
Oh, okay.
Okay, so that's where we lock in, and that's, I think we're the only ones, as far as I know, in the world. I've not seen anybody else do lock in on this. The other advantage with that comes that, since it's a lock-in technique, it makes it theoretically 100x more sensitive. We can now dial down the energy that's being put in.
Okay.
So if you have a very brittle part, you can bring down the energy and therefore not create additional damage if you're worried about that on a brittle part, for instance. So that's
just to add to that a little bit, and kind of to his point, your input signal with the vibrothermography is extremely high frequency. The camera can't match that. But with the right parameters, like what Marcus was mentioning about adjusting amplitude, and you can adjust the period length and stuff, you can kind of tickle out a thermal signal that has a periodic component that's more close to what the camera can pick up. So just because your input frequency is insanely fast, the heat accumulation, the way that, like, I've seen this on parts like that are under the ultrasonic horn, you can see the heat spot sort of glow and then go away, and then come up and glow away, and then that's a periodic signal that the post-processing can pick out and can very clearly show you, okay, that's exactly the portion of that sample where heat is accumulating due to a crack or due to a void, where basically the friction from your input is accumulating heat and releasing it in a way that can be observed.
Interesting. Okay. Wow, that's awesome. I'm curious, because I've heard about, again, I know I'm spending a lot of time on this lock-in technology, but it's fascinating. I've heard of and I've seen customers in the semiconductor space utilizing lock-in and an infrared camera.
Right.
So what might the excitation source be for semiconductor work, and how does lock-in work for that type of an application? A little different than a composite, right?
Right. Yeah, and that's I hope our viewers get the idea how versatile this technology really is for all of these different applications, right? So semiconductors could include solar cells, like photovoltaics, that which branches into thin film, thick film, monocrystalline, polycrystalline, all those kind of things. All of those things are possibilities. And then it goes into actually semiconductors in terms of the wafer level semiconductor. So we have folks that do forensic analysis in failure analysis labs that look at why did this chip fail? How did it fail? Can we reproduce this? They're looking at actually encapsulated components. We can sometimes see thermal effects through the encapsulation even. And then all the way up to a complete functional circuit board and looking for failure analysis there. Let's say you have a dysfunctional circuit board, sometimes just exciting it electrically and just pulsing the power can show you sometimes, let's say if you have a shortcut somewhere, there may be a circuit board trace that's warming up, that's leading to the shortcut, or the shortcut itself heats up. So there's a lot of different cool techniques that you can use for that. We do microscopy on chip level where we can actually see the structures that are like a few microns, and you can see certain components, whether here's the memory location of that chip, or here's a diode, or here's this component or that component, or the bus. It gets there a little bit more involved. The question then becomes, is this a microprocessor that needs a finite amount of time to boot up, to light up certain things on the chip? So then you have to be creative with the excitation. Can you sometimes just exciting the VCC, basically the voltage supply to the chip, might not be good because the excitation frequency might be faster than the chip can catch up with booting up and doing things. So then you may just power the chip up, but then you may be doing some logical excitation where you trick the chip into doing certain functions, like reading a memory location. So you can do a logic analyzer type approach where you exactly tickle certain things in the circuit and then look for the thermal signatures, which are ultra small, and see if there's any abnormal sort of behaviors. And people that are familiar with the layout of the chip will know by the signature, like, is that normal, is that not normal, kind of a thing. Like we looked at radiation hardened chips before that go into space. They're super expensive. They can cost $100,000 plus per chip, and they had they had issues with that. So they can look at things and determine where the issues are, which is super powerful because without this sort of technique, well, what are you going to do? I mean, you can logically try to test things, but in terms of thermal dissipation, with this lock-in technique, you can really pinpoint down to the micron level where the heat originates, right? If you do this passively and you use just the thermal camera, you just see a vicinity of a region warming up. It's almost like a cloudy bloom of thermal, like a thermal blob. But that doesn't tell you anything. If you have 100,000 mini components in that area, like that doesn't tell you anything. You need to know exactly where is that junction that warms up. So typically those things are typically excited thermally. There's some applications where you excite with a laser.
Okay.
But electrically is usually the go-to sort of a thing. You can even do this with a probe station and do portions of a chip, or
And the technique or the methodology is the same as you described earlier about this modulation,
right,
and then operating the camera at that same frequency and just looking at the same signal.
Right. The it's a frequency based. So what you're getting back from it is from a mathematical point of view, you're getting the real and the imaginary portion back of it's an FFT, like a fast Fourier transform sort of a response. I don't want to overwhelm folks that are not too technical, but so what you're getting back is basically you have the stimulus signal, which is at degree 0, and then you're measuring the response, something that warms up slightly delayed. Right. It's basically coming in and creating a phase shift to the original stimulus. So you have that phase angle response, which then on a pixel by pixel basis is converted into a contrast change in the image, essentially. So you're making a phase angle visible by contrast. Again, it's mind bending sometimes when you look at this stuff. You know what I mean?
I'm still trying to wrap my head around this, because when you're looking at the resultant images from lock-in, it's for a passive thermography guy, it's easy for me to just say, oh yeah, I'm looking at a thermal image. I'm looking at, the heat. It's not heat. You can't measure temperature from that lock-in imagery.
Indirectly, yeah. What is displayed is not temperature. It's basically a sequence of images. It's basically a temporal thermal response, but really expressed as amplitude and phase.
Amplitude and phase, which is when you make that transformation, is really when you're teasing out, if you will.
Right.
Yeah, that very small, very fine. You're eliminating the noise and all that background nonsense and looking at.
But you can get very sciencey with it. You can essentially calibrate the phase angle to a microwatt or milliwatt sort of an output. So you can actually use a very high precision resistor.
Yeah.
Like a 1 ohm resistor or something like this with a 0.1% sort of tolerance. You can hook it up to your power supply that you're modulating, and then you can modulate this, and you can see what sort of a phase angle, knowing the voltage that you put in, and by Ohm's law you can basically say what current is going to flow through it. You can calculate the power dissipation and it's 100% power dissipation. So you know how many milliwatts or microwatts it's basically, and then you know what the phase angle is. Now you can calibrate the system, and then you can use that and look at any sort of chip and everything else, and you can say X amount of degrees of phase shift equals 17 microwatts of heat dissipation.
Yeah.
And that can give you now valuable insights, on a quantitative level, and you can use that and calibrate the system that way. So you can indirectly measure heat, if you will, but a lot of people, I get the question all the time. It's like, oh, so what's lighting up is heat. Well, yes and no. It's it's directly related to it, but it's not quite expressed like it. Yeah.
Basically, it's like I usually try to emphasize that one result image, like if you're looking at a lock-in image, the intuition is that happened at a point in time, because we're used to seeing photographs, that were taken, a snapshot in time. These are actually result images compiled from sometimes hundreds or thousands of thermal images taken, during the duration of the measurement. That result image contains basically pixel by pixel insight into what happened during that entire sequence. So not only is the image not really grounded in temperature, it's not even grounded in time.
Yeah.
So that's why, it's a little bit, it takes a while to kind of wrap your head around it. And like, we don't really have a physical intuition for like phase angle of like a frequency, So really what helps me to think about is it's almost like a graph. Like if I look at one pixel and I look at a graph of like, this is, the temperature over time, you do that, for a 640 by 480 image, those are all of your different pixels, and it just happens to produce like a picture.
Yeah. That's
essentially what it is. It's just hundreds of little, little series data points, hundreds of little charts behind every point.
I think that's a very good point. What's also constantly confusing people is they look at it from a perspective of, like you said, it's an image. It's what it really is. And it is signal processing more so than it's image processing, but it's really combining the two worlds, and they merge, right? Which is true even in passive thermography, right? When you look at something, it's more of a signal processing. It's heating over time. If you graph a passive thermal image over time, or like a video sequence, and let's say you're monitoring a motor, electrical motor or something warming up or something when you turn it on, that is basically, in a sense, it's more signal processing than image processing, because what you're really looking for is temperature over time. And here we're doing a complex math on the image, more coming from the signal processing world. FFTs are being used all over the place, and also with audio and everything else.
All over the place.
Right?
Yeah.
And this is now a combination, which makes it even more confusing, a combination of image and signal processing. Really, it's really signal processing on a pixel by pixel basis.
I've been fascinated by this technology, and for those of you who are at my level, sorry, Marcus and Nathan are totally geeking out here on us. But the more I learn about this lock-in capability and technology and the history behind it, and also I was shocked to learn that there's actually what's called a lock-in amplifier, a piece of hardware that's used in the electronic space that does this automatically for you, right? It does all this signal processing and spits out.
Those are usually
the noise. Yeah.
Those are usually single channel.
Yeah.
Imagine that now 640 by 480 times.
And that's amazing.
Yeah.
That's amazing. So if you're intrigued by this capability and you want to learn more, I would encourage you go to the Mobitherm website, and there is a knowledge base library there, and there is some great content on not only infrared non-destructive testing but also on lock-in. In fact, there's a video there by John, one of the employees here, that is probably one of my favorites when it describes how lock-in work. He really distills it down to a basic level for guys like me who can understand. We're going to wrap up here in a little bit, but before we do so, I would be remiss if I didn't pick the brains of these two guys here who have been working in this space and just ask you some questions about, like, what are some of the trends that you see right now when it comes to active thermography, active testing? What are some of the things that you're seeing out there? I mean, we talked a little bit about aerospace. I even led in with an introduction talking about the F-35 strike fighter, and that kind of falls into that category. What are you seeing? Nathan, maybe we'll start with you and then Marcus. So what are some of the things that you're seeing, some of the latest trends? And
yeah, I mean, just because we have a relationship with so many different industries, it's easier to like pick out the commonality, like what are they all kind of asking at the same time? And to me, that's automation. Basically, like, you have your result, using the techniques we mentioned. And traditionally, this is something kind of like a doctor reading an x-ray where you're looking at this result image and a human being has to make a decision, okay, is this a defect or not? We're now at a point technology-wise where we can start having computers do that using, automated image analysis. Not only that, but also the automation of the measurement itself. What if you have a sample where you need to sample, 150 different points on it, and you don't want a human being sitting there, and also repeatability. You need to be able to basically hit go and be able to repeat a very specific coordinated measurement of a complex part over and over again with different parts, and you need to keep more and more things are just becoming like data handling issues, automation issues that we've started to address with our technology.
Okay, fascinating, awesome. Mr. Tarrant.
Yeah, absolutely. We have seen this over the years. Definitely, the need for let's say in the aerospace industry for ever increasing inspection needs in terms of volume of parts and size of parts, where most other NDT techniques do not compare anymore. Imagine, I'm not sure if you ever stood next to an aircraft. You probably have, with your background. Boeing 787, almost entirely carbon composite. I mean, the wing, you can only appreciate the size of the wing when you're standing next to something like this. Just ginormous. And let's say we have to do a full-on 100% surface coverage doing non-destructive testing on the entire wing. If you're standing there with a little ultrasound probe, I'll see you in 4 weeks before you have that covered. Not only that, but now we have the problem, well, did you really cover everything? Where's your reference? How do you know that you covered everything? They're starting to paint little, crosshairs or little grids on it and figuring out, so there's no reference to the spatial, where did I take the image? Everything is just like not built for speed and large areas, where thermography, I can take 3 foot by 3 foot shots, in a matter of seconds. So I can cover this whole thing in a tenth of a time or better. And that's just one of those things. But like Nathan said, the need for automation, it's a difference when I've seen people move around with scissor lifts and taking and manually manipulating the cameras in terms of repeatability, what he said. Now in manufacturing, they have gantry sort of systems, robotic systems, or these articulated arm robots or whatever that manipulate the cameras around. Well, so that needs to be automated because you need to follow the contour of the part. And that's just the image, the automation of the image and measurement taking. But you also need to make, if you have 500 images collected, who makes the decision now whether that's good or bad? So we have the talking about image processing or post-processing now. If it's a very repeatable part, we can now apply image processing techniques and actually find defects. We can add artificial intelligence to it and do detections to say, hey, the other 50 images didn't look like there's something is up here. So definitely the trend goes heavily in that direction. So everybody's like, we need to automate this.
Yeah.
Because time is of the essence, and and especially when you bring the deglobalization that's underway because of the whole supply chain collapse during COVID and still going on and everything else. A lot of these manufacturers are like, it's too risky to produce at 15 places around the world. They want to bring this back into the US, but then the labor rates are so high, you have to bring down the cost of inspecting a part. And the only automation, the answer to that is automation.
Yeah.
Right.
So guys, one last question. We're sitting out front of this IRNDT lab, and Nathan, you mentioned feasibility study, and maybe you could just, as we wrap up here, why does Mobitherm have an IRNDT lab, and what is a feasibility study, and so what, right? Why? Yeah. So maybe we can wrap up with that. Who wants to take that?
Yeah. So so basically, a customer, if they're comparing different NDT solutions, or they're just trying to better understand defect presence in their part, they can send it to us for thermography analysis. They usually send us a sample, and these are coming from all kinds of different industries, samples of all shapes and sizes, and what we do is not so much, it's not really a matter of just, using thermography broadly speaking and, showing them the image, because like we've sort of touched on today, that thermography is a lot of different things. It's a lot of different techniques. What we're really doing is comparing. We talked about different excitation methods, being suited to different materials. So what we do is we kind of try to determine a best case setup. What is the proper excitation source? What is the proper camera? Because there are different cameras: cooled, uncooled, long wave, mid wave. We need to find the right configuration, not just to find the defect presence, but oftentimes customers are working in cycle time requirements. They need to do it, in under 60 seconds, or et cetera. Budgetary constraints are a big one, and so we kind of listen to all these different variables that they're trying to do and come up with, basically, okay, this is what we recommend equipment-wise, and this is what your image, results look like, and then we start that discussion with them, and that's really helpful for the customer to get a sense of, okay, what exact hardware are we dealing with here? How does this technology work? And then once I, set this up in shop, what's that going to look like, day to day?
Sounds like you're helping these customers eliminate the guesswork.
Yeah, it's basically a built-in success guarantee, right? Like, we have a heightened interest to maintain our reputation. We want to make sure we're not selling expensive equipment to a customer that's then frustrated because it doesn't solve their problem. That's a very bad spot. I don't want to be in that spot. I don't want to have to take the system back. That's just not where I want to be. The customer shares the same sentiment. They want to make sure, is this going to solve our problem? Can we detect the defects? And there's scenarios sometimes where it doesn't work because, again, we can't bend physics, not yet, right?
Not yet.
So that's really the reason why it's a very low risk kind of a way to experiment with this stuff, and we learn a lot of times. We learn still after years and years of doing this, what works, what doesn't work, what works better. Just imagine the decision of saying, hey, you know what, your application actually works with an uncooled camera. Guess what? Your system, we just knocked off $50,000 off your system price. Was it worth it? Well, I think so, right? Would I like to sell the more expensive camera? Of course I would. But if good is good enough, I'm not going to do that. And that's part what comes out of the feasibility study, is that conclusion to say, you know what, this works well. So let's go with that. You know what I mean? So those are just one example out of many why, certain things work like this. And we have sometimes we get samples sent that are quote unquote known to the customer. They're like, oh yeah, there's 4 defects in there. We look at this, there's 6 or 7 they didn't even see coming. They didn't
or
even
an entirely new defect type.
Yeah,
we've seen that a few times where we're showing them results and they're like, I have no idea what that is.
Yeah,
and so you start that conversation with them, that kind of like relationship where now all of a sudden, like, we are trying to answer a question, we're sharing a question. What is this thing? And we have like the tools to investigate it.
Yeah, I'm looking here in the lab and I see, what is that, an ultrasound horn? There's a cooled camera over there. I think I saw an uncooled camera. There's light sources, halogens. It's like a xenon lamp. So you have everything right here at your fingertips to run all these different scenarios.
Right.
Essentially developing the recipe for the customer.
Right.
To solve their problem. That's amazing.
Yeah.
And I know I've already mentioned once before, if you want to learn more, go to the Mobitherm website. But if you want to learn more even about feasibility studies, how do they work? What are the steps? How do you initiate one? That's on the website as well. So I'd encourage you, if you're interested, to go there. And of course, you can always reach out to us directly anytime.
Yep.
But
do we have a Twitter? Do they tweet us?
They tweet us. They
call
us.
Mobitherm,
Yeah. I think that wraps things up though for today's episode of the Thermal Review. We covered a lot.
Yeah.
We could probably break this down and
and we really just scratched the surface.
I know we did. And that was the objective, that we
Right.
really wanted to just kind of introduce at a high level the difference between, again, passive and active thermography, introduce the different techniques, and then talk about excitation sources, and then also kind of what the latest trends are, which is pretty amazing with regards to the automation.
Right.
So thank you again for joining us for this episode of the Thermal Review. In our next episode, and I would encourage you to join us, we'll have another guest speaker with us next time. Actually, Jerry Beanie from Teledyne FLIR. He's the Global Business Development Director there, and he's going to join us, and he's going to be talking about some of the latest advancements in infrared cameras and how that's affecting our IR NDT capabilities, some of the advancements and things that Teledyne FLIR is developing. So you don't want to miss it. Nathan, please come back. You can sit in with us and learn from Jerry. Please make sure that you subscribe to us, to the podcast on iTunes or Spotify. And Nathan, any last comments, words, suggestions?
Tweet us. We want to hear your thoughts. Hear some. Let's get a conversation going. Send us your questions. We love answering questions. Like 90% of what we do.
Right. Also go to our YouTube channel. youtube.com/Mobitherm. There's a lot of educational content on there, especially also with respect to NDT and other thermography topics. That's also another great resource.
Awesome. Excellent. Thank you. Thank you to our staff, Michael and Yadira, for producing our podcast series so far and going forward. Take care. Bye-bye.